Hello everyone, welcome to the Focus on Microscopy 2021 online tutorial.
Welcome to
It
the
is my
Focus on
greatest
Microscopy
pleasure to be here
2021
today.
online tutorial.
Although due to the pandemic,
It is my
I
greatest
cannot
pleasure
meet
to be
with
here
you
today.
face to
Although
face.
due to the
So today
pandemic,
we're going to
I
learn
cannot
about
meet with
optical
you
microscopy
face to face.
simulation with
So
Matlab.
today
My
we're going to
name
learn
is
about
Peng Xi.
optical
I'm
microscopy
a full
simulation with
professor in the
Matlab.
College of
My
Future
name is Peng
Technology in
Xi.
Peking University in
I'm a
China.
full
And
professor
I
in
am
the
also
College of
affiliated
Future
with the
Technology
College
in
of
Peking
Engineering,
University in
Southern
China.
University of
And I
Science
am
and
also
Technology
affiliated with
in
the College
Shenzhen
of
in China.
Engineering, Southern University of Science
And
and
I am also
Technology
an
in
managing
Shenzhen in
editor
China.
of the journal
I am
Light
also
Science
an
and
managing editor
Applications.
of the journal
So before we
Light
begin,
Science and
please
Applications.
open your Matlab and
So
Fiji.
before we
In
begin,
Fiji, please
please
make sure
open
that
your Matlab
under the
and
Analyze,
Fiji. In
you
Fiji,
have
please
the
make
Quick
sure
Home plugin installed. One of the advantage of this virtual conference is that it is pre-recorded so that you can pause me and you can stop at anywhere you wish and then continue when you're ready. So now let's begin. Today we're gonna simulate the following techniques. First, wide field fluorescence microscopy, and then single molecule localization microscopy, and also scanning near field optical microscopy, confocal stimulated emission depletion, and image scanning microscopy, as well as structured illumination microscopy. So I believe you have seen a lot of videos, images about the comparison between confocal and the STED microscopy, in which you can see that the super resolution microscopy gives you unprecedented resolution improvement. And here is a comparison between the wide field and the storm, which is a type of single molecule localization microscopy. So let's temporarily take the super resolution image as our ground truth. So each biological specimen is labeled with many tiny fluorescent molecules. The problem is when we use a microscope to view the molecules, each molecule is spread due to the limited resolution of this microscope. And now let's prepare the image for our next use. So we're gonna first open this storm image, which can be downloaded from the link here. And okay, if you drag it into the Fiji, you can see it is here, and then you select the region of interest, and you click image and crop, and then you get a cropped image here, in which you can save it. But I have already saved my version, so which is here. Okay, now that we have this image, you can store it into, for example, save it as an JPEG file. Okay, I believe you are familiar with that. Oh, before you do that, I wish you to do one thing. Convert the type to be an 8-bit file. Okay, now you saved that and rename it. For example, here I give it a name dstorm.jpg, which I will use it further as my ground truth. Next, let's take a look at the sample. We understand that a point can be mathematically described as a delta function. And if for each specimen, it can be decomposed into many delta functions in a way like this. So the physical meaning of the above equation is we can regard our sample as the sum of multiple delta functions. We can actually decompose everything into delta functions. And imagine a digitized image with many pixels. This image is composed of pixels, and each pixel, which is the smallest element of our digital image, can be regarded as a delta function. And this equation, as we can see here, x0 scans across minus infinity to plus infinity, and so to the y0. We can see that the delta function actually scans across the specimen line by line from the beginning to the end with the delta function. And we can define this whole equation as a term of convolution. So convolution means a physical expression of the f and the delta. And we can understandably see that if you convolute a function with delta function, you get itself. So before our microscope, the specimen is composed of molecules. And after the microscope, each molecule becomes a point spread function, becomes a blurred blob. And if we have two spots or 2 points, it is 2-point spread function. And if we have multiple points, it is converted to a sum of all PSFs. So how to describe this in a mathematical way? We can see that the PSF is actually an response of an impulse or an input of the delta function. And the PSF is the response of the impulse of a system. Here the system is referring to our optical microscope, but in the electronic system, it's the same way. And so to the mathematical description. So if we compare these two equations, we will find that we will simply replace this delta function with an PSF. So in a linear time invariant system, we can safely replace each delta with this PSF and then sum up them together. And the resulting image is the response of the system. Here, the optical system. We can see that the resulting image is the specimen convolutes the PSF. Whereas if you convolute the specimen with a delta function, you get the specimen itself. So first, let's take a look at the wide field microscopy. So in wide field microscopy, our specimen is illuminated by a uniform illumination. And if I use time to describe the response of the illumination and the specimen, I can say that my illumination is all 1, is a matrix of ones. And then the sample can be described by a function, here a 2D function. And the camera gets the response of the sample illuminated by my wide field illumination. So the sample times 1 gives me the illuminated specimen. And imaging, we can see that we can split the sample into multiple dots and replace each dot with PSF, or we call it convolution, described in such a way. And let's run a simple simulation. So here I was trying to generate a 2D matrix with size 512 by 512, and then I try to ignite two spots with the distance 2D. So the center of 512 by 512 is 256. So so here I put the ground truth 256. Let's write this program together. So my ground truth equals to zeros 512, and I will ignite two spots. And setting the D to be, let's say 10. And let's take a look of my image. Okay, let's run this script. Temporarily, we term it wide field 1. Here, why it doesn't pop up? Show ground truth. See? The name. The name is okay. As you can see here, I have two spots. And now, if I change the distance, of course, you will find that the distance changes as well. And next, we will generate a point spread function, and we will convolute it with the ground truth. So my PSF is like a Gaussian with size 20 by 20 and with distance 3, and my image is the truth and my PSF, and I will keep them the same size. So here I will generate my wide field image. As you can see, the ground truth, because my point spread function is too large comparing with the distance between them, the wide field image is blurred. They cannot be discerned. So one way is I can increase the distance. Let's clear all, close all the image, and the CLC is the clear the screen. So let's run it again. Now it is separatable, but if I change the distance to be 5, Okay, it is connected, as you can see, and further shrinking the distance between them, they become undiscernible. So here I have simulated the effect of wide field illumination. And let's also take a look at the point spread function. Here, as you can see, my point spread function is shown here. And it is, because I have two spots, it is convoluted to two places. What if I just ignite one spot? Say I commented this line, I only see one point spread function. Okay, so just for you can copy this line also showing here to um, give you a better comparison of the convolution between spot and the point spread function. Of course, so here, next, I I'd like to introduce the scanning near field confocal optical microscope, or SNOM in abbreviation. So in SNOM, which is an invention by Eric Bettig and Robert Chester back in 1993, they use an fine tip of optical fiber. So a very tiny optical fiber, tapered optical fiber, to scan across this specimen to obtain an image. And because the tip of the optical fiber is much, much smaller than the optical resolution, you can get a super resolution, or resolution beyond the diffraction limit, through the collection of the evanescent wave, which only appears close to at the peripheral of this specimen. So let's try to do that. So scanning the specimen across our specimen. So here I give two iterations, and I will put do a line by line scanning, and I will record everything I scanned into an 1D detection function, termed the DET1D, detector 1D, and so ground it will equivalent to the IIJJ, the same coordinate, and then I reconstruct the image in the same way. So let's do it together. First, I have to know the size of M and N. I will put it there for future use. For II, it is 1 to M, JJ 1 to N, detector 1D has m by n in size, is an 1D matrix, and its coordinate equals to ground truth of each. Okay, so here I will save all the scanning results into an 1D matrix called detector 1D. And when I re when I reconstruct it, SNOM equals to this one, and figure image shows SNOM title scanning near field optical microscope. Okay, now we can comment the PSF line and let's run it again. Oops, there is an error. Let me see. Oops. Sorry. Forget it. Oh. So, of course, there is only one spot. Let's do 2 spots. SNOM can faithfully represent the image that I want. We can add some little function. Ground truth equals to read the storm that we just read the storm.jpg, and we comment this line, and then comment all those. So we have we will read an new image, and we will run the wide field illumination. This is the wide field illumination result, and the SNOM result. Of course, here 3 is too small, so let's put 8 here. 2020, maybe 40. Okay, because I have clear close all, it will clear the history and close all the results. So you see a blurred image, original image, blurred image, and the SNOM recovers the image for you. Okay, so if you compare the original raw data and the SNOM, of course they are identical because of the sufficient resolution provided by the near field optical microscope. Right. Next, let's run some simulation about igniting some of the part of the particles, just like the what's done in the single molecule localization microscopy. So we will read in this image as we have done before and resize it, and then we will randomly ignite several positions, for example, 1,000 positions. And it's like a raindrop onto this image, and if there is molecule, it will be ignited. So it's fully random, a random process, and we will use an point spread function to contaminate it or to blur it, and then do the convolution. So let's do it again, and you will understand what I mean by this. Let's say I want 1,000 spots, 1,000 geometries to be ignited. So II will equal to m minus 1 times RND. So the rand will give me a random number starting from ranging from 0 to 1, and times m minus 1 plus 1 will give me an coordinate from 0 to m minus 1, and then after plus 1 will be 1 to m, and so to 1 to n. And because my number is 1,000, these two settings will give me a coordinate group of combination of 1,000 possibilities. So next, for kk, it is from 1 to none, and jii jj equals to 1. Give me all the so I search all these locations. So first, j equal to zeros, m by n, and then I ignite all this, and so here I should choose change the wrong choose times h, and then I will show the g, respective g and h, and you will see what I mean. Or what I can do is I can, yes, resize it to 512 by 512 to save some time. Forget one thing, to change it to be a double. Comment so here we should notice the type of the here, not 512. Here. All right. So I have rescaled my ground truth to be 512 by 512, and the wide field, by the way, we should compare it with the original file. Let's do that. As you can see, it's quite comparable. Although less noise as of the wide field, true wide field, but the resolution scale, it is quite similar. We can now simulate a more blurred or less blurred wide field image now. Okay, and because this is the a time the ground truth times the spots, we have only a few spots left because of this modulation. All right, now we have this modulation. We can do a batch of such modulations, and let's say for a proper home storm image, you typically will record somewhere between several thousands or tens or hundreds of thousands of images. So for the time being, we can do a batch process for that. Okay, let's I'd like to change a little bit of my code. So here let's run 1,000 times, and we have this one image, and for each image we will ignite 1,000 molecules. We can adjust this just like illuminating more or less light to suppress the molecules to be on the so-called single molecule state. And because we will use an optical microscope to collect the image, we will just how to say, we will blur the image with an convolute to we will collect a wide field image. So this is the H1 is our wide field image, and we will use another buffer to store all this image, and we will convert this each image stored in H1 to be UNT8 so that I can so that I can properly show and to show and to save it. Okay, and control I gives you a nice look of the code. So iteration 1,000 times. Okay, for the time being, let's do it 10 times. And show H3. Oh, here I forget one thing. I will make this PSF to be normalized. Okay, now the maximum of the PSF is 1. And then do the convolution, and then I will show the image. Let's see what it can give us. And for the time being, I don't need the storm. So let's comment on that part and run. Uh, an error occurs. Let's see what's it. Oh yes, I forget. As you can see, the image starts. Let's run 1,100 times. And after this blinking, I can sum of single molecules. Okay, as you can see, the sum of the single molecules is quite similar, but not the same as wide field microscopy. Okay, this is a result of 100 iterations. Certainly, we can save all this, all the generated image by using imwrite. These folders and single molecule localization microscopy 1 and the num2 str iteration dot tif. Okay, because to show the image is slow, I will comment on this line. And so here, it will save all the image. And I will add a little function, which is called a wait bar, so that when we wait, we will see something. Wait 1 equals to wait bar 0. And during the save, iteration divided by 1,000. Here I'm gonna run 1,000 times. Wait 1 and okay, and after that, I want to close the wait bar. I will save it to a different folder so that you can see what's going on. And I'm gonna copy and paste it to here so that you find that, okay, I don't have the folder previously. Let's run. Let's see. If you go into the folder, you see it's stored in a folder. I hope this time it works. Yep. If you go into the folder, you see it's storing all these images up to 1,000. Okay, and the program is done. So once it's done, we can find the folder. We can do a lot of things. We can find this folder. We drag it into the image.j, and it says open all 1,000 images. Yes, that's exactly what I want. And if you play with it, you will see the same effect as what I have demonstrated by using imshow, but now I'm using Fiji. All right. Plugins. Now analyze quick palm, analyze particles. So in the analyze particles, I will say, okay, minimum signal to noise ratio 3, quite good. Maximum full width maximum. My pixels are quite large, so I'd say 20 would probably be enough. And image plane pixel size, let's say 50 nanometers. And okay, let's run it. As you can see, out of those molecules, it is building up all the maps, generating the reconstructed image. Okay, and here pops up the results of a single molecule localization microscopy so the intensity position of each pixel is recorded in this data sheet, and you can click on file save as and to save it as an CSV file for later use. Okay, close it for the time being, and if you change it to an 8-bit and adjust the brightness by clicking on auto, you will find that this image is quite similar to the original ground truth that we have set up, except that we don't have enough sufficient molecules to localized so that to represent it. I believe the other talks, the other two tutorials gives you nice overview of that part. So we will not go in too much in detail on that, but you learn the principle of single molecule localization, what is going on here. And of course, you can um, do something different, change a few parameters. For example, here, why don't I ignite more positions, or maybe less? And I have record different number of iterations. For example, let's say 5,000. And so after a while, you get all your data. It is accelerated if you don't use imshow to show this. So that's why I commented this line to show. But after storage, you will have all batch of data. Let's see how it progress. It is working slowly, almost done. Okay, now it's done. And let's close the original one. Redrag it there. Open all 5,000 image, yes. may take longer time because of the data density. Now it is more single molecule, but this blob is quite huge due to the fact that I choose PS of 8. So in analyze quick palm, analyze particles, maybe I will set this to 30 and the signal to noise ratio 2.5. Okay. Yes, replace the file. .2 file to build up this all these modules, I must say. After that, we get a much denser map. As you can see already now, of all these molecules, their possibility to appear. And of course, if you're interested, you can load other types of to demonstrate the field and as well as single molecule localization here using the same technique. All you need to change is to ground truth equals to read a different file. We're almost there. Okay, a huge map. I won't save it. So yeah, I have done a different demonstration of that. After that, we get a much denser map. As you can see already now, of all these molecules, their possibility to appear. And of course, if you're interested, you can load other types of to demonstrate the field and as well as single molecule localization here using the same technique. All you need to change is to ground truth equals to read a different file. We're almost there. Okay, a huge map. I won't save it. So yeah, I have done a different demonstration of that. Okay, I won't save it. So next, the PSF. As you know, the PSF can be expressed with an Bessel function of the first order as this, where this v equal to 2 pi over lambda Na times r, and the Na is our numerical aperture of our objective, which is n times the sin alpha, and in which here alpha is the angle of the focal angle, and r is the radius of the point of interest. So we can plot this this function by writing a very simple PSF function here. So the PSF function y equal to PSFx, and it is equals to ABS 2 times Bessel j to the first order 1x over x, and the 1 equal to temp times temp, which is the square of the temp, because it is an ABS. So once you have this PSF function, we can plot the PSF. For example, here I give you a range of r equal to -2 to 2 nanometers and with the distance 0.001. And YY equal to PSF. And before that, let's do one thing. Clear all, close all, CLC. And the reason to do that is I often term it PSF in both 1D and 2D, and sometimes the computer gets confusing. So RR times 2 times pi plot RR YY. Let's see what's the PSF in -2 to okay, it gives you the PSF file. Next, let's move it to the so-called Rayleigh criterion. So 1 move to 0. So the Rayleigh criterion denoted here is D equal to 0.61 lambda over NA. So let's give it a coordinate of 0.305, which is half of 0.61. And the other one is plus, and we plot the first one, hold on to plot the next one in red. And we sum them up in 1, 2, and plot into black. And let's run and see. Okay, here gives you the so-called Rayleigh criterion, in which the 2 spots were separated by a distance of 0.61 lambda over NA. And we can see that we can see their shape and the sum of these 2. And we can rename this part as Rayleigh and title it Rayleigh. So my exercise is I'd like you to move the 2 dots with distance as Abbe diffraction limit and the spiral diffraction limit. So generate the so-called Abbe and the spiral cases by just changing the previous code into different distances. Now you can do it, and you don't have to watch me. For Abbe, it is 0.51. So if you divide 0.51 by half, it is 0.255. And for a spiral, it is 0.47. And divide by half, it is 0.235. And if here I have used a function called subplot, and to generate a subplot of 1 by 3, and I will put first, second, and third into respective places, and after running you get this result, right? Here the distance of Abe is actually 0.5, so the full width at half maximum. So the two spots were located at the full width at half maximum of my PSF file, whereas for spiral, it is set up at, it is another criterion in which the sum of them doesn't have this little dip as in Rayleigh and Abe. So the spiral actually shifts from Abe's 0.51 down to 0.47, and you get all the results. By the way, spiral is more an and criteria mostly used in the astronomy, not in microscopy. All right. So next, let's take a look at the wide field versus confocal laser scanning microscopy. So in wide field microscopy, we illuminate the entire specimen, and we use a 2D camera to record this image, which is a response from and after an objective. And in confocal, however, we only illuminate one spot of the specimen, and we use a focal spot detector such as an PMT to obtain the image of an to obtain the response from this very spot. So there are three conjugated focal spots: the laser, the illumination, and the detection spot. We can well understand that the laser being a point after this microscope will be converted to a PSF, a point spread function. But how about the pinhole? If you shrink the pinhole really, really tiny into a spot, you will find that if you can illuminate from this pinhole, it will also generate another point spread function here. So actually, the result of confocal is the PSF excitation times the PSF of detection, because we can reverse the light beam and get the proper answer. So for illumination, it is sample convoluted by a PSF, and the imaging is quite different. For a confocal with small pinhole, it is the square of the PSF, because the small pinhole functions as an modulation function of the excitation PSF. And if you widely open for a large pinhole, however, the PSF detection becomes all one, just like a wide field case, and your resolution is determined now by PSF excitation. I should change the equation slightly like this. The PSF excitation and the PSF detection simultaneously determined the resolution of a confocal. And if you have a smaller pinhole, then your PSF excitation and detection would be the same. So times it, your PSF is narrowed down and you get a better resolution. However, if your PSF detection is a constant one, meaning your PSF detection is widely opened, you cannot improve your resolution any further. You will, but you will only get something similar to an wide field result. And we will test that, simulate that effect soon, very soon. But let's now move on to the stimulated emission depletion. So in the stimulated emission depletion, we use an donut state pattern to modulate the excitation fluorescence, and it will drive the molecule from the stimulated fluorescence state into stimulated emission. And then we use a filter to filter out the stimulated emission light, and the leftover is, or the effective pixel PSF is shrinked down, which can be nicely documented into this equation. And in this equation, we can see that if your saturation light, if your in the intensity of your steady light is very strong, or your saturation is very small, you can get a better resolution enhancement. And from a confocal conventional resolution down to a steady imaging result. And your effective pixel, as shown here, can be improved by the steady process. So so in order to simulate that, we need to simulate both the excitation PSF and the steady PSF. For the excitation, we already know the way to simulate it. But for the steady PSF, it can be simplified as an first order Bessel function, but not divided by the x itself. So we will modify our PSF function here by simply change it to a first order Bessel function. And we will similarly plot it. I can comment all this. I can only use one spot. And I plot it. This is the excitation PSF. This is the steady PSF. And what I'm gonna do is I'm gonna define a saturation factor of 10, and here yy12 becomes the yy divided by square root of 1 plus saturation times the yy2, which is the stat. And I will plot the result and title STED. Okay, as you can see here, my original point spread function is here, and if I give it a stat with saturation factor of 10, it will give a better resolution, and further increase the saturation, we're gonna have a much better resolution likewise. Okay, now that we have simulated the stat result, and as you can see, it is only a different type of confocal microscope. We will not extend that on that direction, but we will do a confocal scanning. Previously, we have done some scanning in the snow simulation. You remember that? But we haven't really extended to a confocal case. So in confocal case, you remember that our excitation would be a point spread function, which expands several pixels. Now we will define an area, and then we will scan across this area. So let's go back to this. Now we will reuse the snow result. Let's save it to a different file, wide field, and confocal. We'll delete that. So once again I need an detector 1D, but now I need first to have a small piece of my image, a sub-image generated from the original ground truth image. And so I have written a function called myGaussian, and the input is AA, II, JJ, and PSF. So the AA is the original image. This function written an II by JJ sub-image from this AA and multiply it with the PSF function. So the way I do it is n equal to size PSF by n equal to size PSF, and I take the first index, and y equal to AA II minus floor n by 2 to II plus round n by 2 minus 1 JJ to the same. So I cut a square close to the geometry of II JJ by half n to minus half n to half n, and JJ minus half n by half n, and this would be the same as my PSF size, and then I use dot times PSF to modulate it with the PSF. So my PSF, as you can imagine, it's like a Gaussian, it will illuminate the central IIJJ and adjacent pixels. So here I'm simulating this phenomena by using it. And you need to have this code here. Save it to a separate file. And once you have done that, we will modify our. Previously, I am only taking 1 pixel, but here I need to take an area of pixels, and to avoid the if I scan to the border of the image, I run into some trouble. So here I change it. Let's shrink a bit of my PSF so that I avoid the troublesome border effect. And -10. So each detector 1D would be a sum of. It is an the PSF. This PSF will be the 2D responses. My Gaussian ground truth. I have to give it and with the same coordinate. And once I excite and once I take this small region out, it is further modulated by the PSF of confocal detection. So let's say PSF detection equals to my PSF excitation. And then I will have 1D detection, and my confocal image will be the same as this. Okay, let's try it. Yep. Okay, this is the wide field, and this is the confocal result. here. I made a mistake. Catch the bug. As you can see, confocal gives you slightly better resolution ground truth. Wide field confocal. Confocal gives you slightly better resolution over the wide field counterparts. And what we can do is if you set the PSF detection to be all 1, then you will get the same response as your wide field. So your wide field and the confocal will have the same resolution by now, by doing so. Okay. So let's summarize for our part 1. The sample can be regarded as multiple points or delta functions, multiple molecules, fluorophores, you name it. And each molecule, after the microscope, they spread out as the point spread function. And so the convolution is a process to replace each point with your point spread function. And in a linear time invariant system, like usually we regard our optical microscope as a linear invariant time invariant system or spatial invariant system, meaning at each coordinate your point converts to the same PSF. The convolution replaces each point with a PSF. And wide field is a simple process to convolute the specimen with the system's point spread function. In confocal, it is more complicated. If with a smaller pinhole, because your point spread function of your detector equals to your point spread function of excitation, you get an PSF square here. And it can be translated as a better resolution. Because the PSF takes a Gaussian form, you can easily find out that the resolution can be improved by up to square root of 2. And for a large pinhole, the PSF detection becomes to be 1, and you get the same expression as in wide field. So you scan your specimen across the PSF, and you get the same result. We can run the simple test. So here, once again, I ignite 2 spots, and we use the same wide field image, and we do 1 wide field, 1 convolution, and it is stored one into wide field I, and the other into confocal. Let's run it. Yes, I should not have this line. So, okay. Let's see. Oh, I forget the distance. Distance set to 8. Okay, the point spread function, the width, I set it to be 15, maybe too small. So I will rescale this. Okay. So wide field confocal, they look identical, but whether they are really identical, I'm gonna do this. I have a new matrix called AA. And I will show it. It is purely blank. So you can see it is a really a zero, that meaning I equal to the confocal, the wide field equals to the confocal in a wide opened aperture, and I scan across the specimen like with that. And we have also talked about scanning near field optical microscopy, which is I use a semi-delta function to scan across my specimen, and also STED, in which the STED is nothing but with a better confocal PSF. Once you can generate a smaller PSF to generate such effects as confocal versus STED, what you can do is you can, for example, now that I know confocal is STED is nothing more than a smaller PSF, we can add a few lines. Run this section, and you will find that, okay, STED really gives you a better resolution over the confocal counterpart. Okay, that's all for part one. I hope you enjoyed this part, and let's take a 10 minutes break, and we will resume afterwards. Thank you. Okay, everyone, welcome back to the Focus on Microscopy 2021 online tutorial, the second part. So now let's begin our simulation. As many of you have heard about the technique termed image scanning microscopy by Jörg Edelen in New York Augusta University. And in that technique, it is the physical principle of image scanning microscopy is similar to structured illumination microscopy, in which both techniques can provide us twice resolution improvement. But here, image scanning microscopy, scanning and imaging the confocal pinhole using an EMCCD camera. So the optical beam path is shown here. Looks like complicated, but if you follow the excitation, beam splitter, dichroic, and then the scan mirror, and all the way through the microscope objective, and when it passing by, it goes back to the confocal aperture. So this part is identical to the confocal microscope. Yet after the confocal aperture, instead of using a PMT or APD, a point detector to detect and scan the system, it detected the the image of this pinhole using an EMCCD camera. We're not going into too much detail about the principle of that, but we only do a few demonstration of the of that principle. So before doing that, please draw on a piece of paper a confocal system diagram by yourself. And once you finish, you will find that in confocal, your point source will generate a point spread function. And like just we taught previously, your point detector will generate another point spread function as well. But this point spread function is a virtual point spread function. It modulates the real point spread function. So next, what if we replace the detector pinhole? What if the detector pinhole is shifted? We're going to use Matlab to simulate this part. So let's open our Matlab. And previously, we have simulated about the point spread function by generating really criteria, IB criteria, etc. So we can modify a little bit of this point spread of this chart. So for example, if we find here, if we modify it to be minus 1 on the minus 3 and the other one y2 on the plus 3, and no, we will put it to the center. 1 on center, 1 on the positive side. And we will show this two chart. And the new chart will be their multiply. That's all. As you can see, the ISM locates actually on the half of their if let's regard the blue one to be the excitation and the red one to be the detection, then the result PSF is only half of the product of those two. So bearing that in mind, the image scanning microscope regard the image scanning microscope first regard each CCD detector as an shifted pinhole, and it need to shift back to its original position. So the way to do so is by shrinking the size of the detected image. So in one image for one scan position, it is located here, and for the detector is then shrinked by half, reduced to half size, and contribute back to the ISM's image. And it works like this. So the upper row is the one-to-one mapping, which is like a conventional confocal microscopy result. Here we use a 2D detector to detect everything, and then we put back what we have on the 2D detector to its position. But in an one-to-one half mapping, in which is what the image scanning microscopy do, we detect it as an point spread function, and then we reduce the size digitally by half, and then put it back to the image. Okay, let's simulate both this and this scenario. So we're gonna open what we have on the previous class. So this is what we have for the confocal scanning. But here, because I want to do an ISM detection, I need to have a 2D detector and detect it by m times n snapshots. So I'm gonna have detector 2D, which is an zeros. Each detector is an nh by nh by m times n uh, of, of the size. So here, referring to nh, my nh is 15, which is the size of my PSF. Okay, I'd like to. Okay, so I detect each of my PSF. And I put it into when I scan, my detector 2D works. So this is the image, and on which image? On the same image as the detector 1D is. It equals to the convolution of copy. It's here. Because it's a 2D detection, it will be convoluted by the PSF. Okay, now I have the detector 2D as my detection. So next, we can generate an confocal putting back, but with the same as the confocal size, what I detected. So here I define ISM2 as the same as my original image, and I'm gonna copy the confocal part, but instead of putting on the detector 1D, uh, here my ISM2 will I will allocate a small part of the image, which is this part. And I'm gonna put it back to where ISM, because it's an image. I need to give it a range. J minus 7 to JJ plus 7. So this is my ISM2. I'm gonna take a look at what it looks like. Oh, here I forget one thing. It is an accumulated process, not just equal to. So it has to be summed up on top of that. Okay, once again. Okay, let's see, ISM2. Oops, here. I simply putting it back to the same position as the original ones. So next, I'd like to shrink the size by half. And the way I do so is I'm gonna reduce the size of temp. Resize it by half. And I'm gonna put it back to here. Reduce the size image. It is my ISM. And during that, I can actually also change the two dots into an real image. I'm going to give you a demonstration about using the cameraman. Mm. Comparing with the ISM2 or the confocal result, my PSF is indeed shrinked by half. So I'm gonna run you a demonstration. Here I give you the full experience of both using ISM, in which I use image resize to reduce the image, and I'm going to read in and the cameraman. Um, and I do the ISM2 reconstruction, and let's do it together. So we can set up and a stop point and run it. So we're gonna move it line by line. So mn equal to size AA, which is I read in an image and convert it to double and give it and read its size, and the NH width I generate my PSF and put it back to HH. So here H confocal equal to 1 means an opening pinhole. H confocal equal to HH is my H confocal means my confocal modulation is an infinitely small small detector, small pinhole, and then detector 1D and detector 2D, the same as what we defined. Move on to this stop, and this is the confocal, and this is the ISM. Move on. So for the confocal we are familiar with, and for the ISM reconstruction, it simply reconstructs, and then the ISM2, and so last part is ISM4 reconstruction. I'm gonna explain the ISM4 by giving you the literature about rescan confocal microscopy. It is scanning at an so in confocal we scan at a state, and then when we do the D-scan, we're going back in the same to the same galvanometer so that it is D-scan. But in rescan confocal microscopy, it is scanned by another theta. So altogether, it is two theta. So the principle of this technique is for a confocal, we scan and then we descan, or we go to this pinhole. But we when we're doing a rescan, we use another scanning mirror to scan it, to scan the image of this pinhole to a newer position on 2-theta. And the result is that you can, by scanning it twice, 2 times the angle or twice the position, you will be get an separated image. So the code here is very simple. We generate a larger size of the image, such as this ISM4. I give it an twice m twice n, and then I put back the detector to this coordinate into the same as the ISM2. And however, here because I give my I have enlarged my size of the image, so ISM2 will generate the same identical result as my ISM. Okay, without further introduction, here is the ISM4 rescan confocal microscopy does. So I'm gonna continue it, and it will give you all the results. So if you pop up this, you can see that for a confocal, it is blurred as much as your wide field. And yet for ISM, if you see the eye, the mouth of this man, or the content on the camera, you can see that ISM gives you a much finer detail, and also to the ISM4. And ISM, regard of the ISM2, because it is a 2D scanning, but it puts to the same coordinate as confocal. So for confocal, it is an point detector 0D, and for ISM2 is a 2D, but the image quality or the resolution is identical, but ISM gives you the same image resolution as rescan microscope. As a matter of fact, I should change here the title to be rescan, and I can change all the ISM4 to be rescan. Shift enter. Yeah, that's a much better practice. Okay, next we're gonna take a look at the 4F systems. So you know 4F systems. If you put an arrow here, um, it will give you an inverted image on its conjugate plane. But what's going on the Fourier plane? And you can draw the geometry optics by following the following two rules. The first is the point at focal plane generates parallel light beam uh, after the lens, and the light passing through the optical center of the lens doesn't alter its direction. So let's say for this one, it becomes a parallel line. And because this parallel line, um, it has the same line as the light from the center. So we connect the point with the center. We will give this line and draw two parallel lines like this. And following the same two rules, we will have a focal spot. Whereas for this one doesn't we connect this one with this one, this point, this optical center, and it doesn't alter its direction. So we generate another parallel line, and it will further, because this line passing through the optical center, it will form an focal spot somewhere on the focal plane, which is here. So we're gonna if you connect these two dots, you will find an inversed image. So we will simulate this portion. We will find what is going on the Fourier plane. So in the Fourier plane, it actually generates an Fourier transform, and we will use Fourier transform to simulate what we have. What I'm gonna do is I'm gonna have a sample. Okay. So with an width equal to 10, and I create an 1D array with zeros 1 to 256, and from D to 200 minus to D equals to 1. So it's an aperture with width of twice the D. And next, I'm going to calculate the FFT of this aperture and shift it and put it to FFT and I will plot the AA and its how to say its Fourier transform. Okay, as you can see, so here is the F from D to 256 minus D, it is 1. So I can open an broader or smaller aperture, and the conversion of it gives me the how to say gives me the the point spread function of this object. So previously, as you remember, instead we need to modulate and generate a hollow donut shape. How to do that? Actually, instead we're using an 0 to 2 pi vortex faceplate. This vortex faceplate gradually changes it from 0 to 2 pi by a rotation of 360 degrees. But if you cut this vortex into half, you will find that no matter which direction you cut, it is always 0 and pi phase difference. So if you simulate this 0 to 2 pi phase difference, you can see that if I give the first half to be 1 or with a 0 phase, and the second part of with a phase of pi, and then I do the same trick of my FFT, and let's see what will happen. So as you can see, my modulated result from D to 100, the transmission is still the same. It transmits everything, but bear in mind that if you plot the phase, it is half difference. And the central part, you will generate a very deep zero donut on top of in which where it originally was the highest intensity. So this is how STED generates a very tightly focused focal spot on the Fourier plane or the focal plane. When you illuminate a parallel beam into it, it generates a focal spot or a PSF or a donut PSF. And this part of the code actually it reads in an image, and if you see the FFT2 actually gives you the focal Fourier plane, and then you further transmit it to another Fourier plane, you will get an inverse image, and we will see the inverse image by running this portion of the code. Okay. Let's close all the image and do the demonstration. So okay, now we are clear. So as you can see, AA is the original image which is upright, but BB, because I do twice of the FFT, it is inverted. So this gives you how you can pass the optics to its Fourier plane and to its next Fourier plane. Okay, next we need to learn a bit more about the sampling and the Fourier transform. So to sample is very simple. It multiplies and delta. And similarly, if we wish to sample it theoretically, we can multiply multiple delta functions of it, and we can define this as a comb function. And in wide field, as I have mentioned earlier, it is a sample times once with the same the sample times 1. But in frequency domain, it is a Fourier transform of everything, and the times becomes convolutes. So the sample is convoluted by a delta function. So as we remember earlier, if you convolute anything with a delta, it actually gives you the original image. And if you convolute a delta, but its center is not on the origin, then it will be shifted toward the center of this delta function. This is an important message that we need to remember. And for imaging, it is an convolution process, as we have demonstrated. And in the convolution, if you do the Fourier transform of S, you get this one. If you do the convolution of this PSF, you get the so-called OTF, which is the optical transfer function. And the convolution becomes a times into in imaging. So it is very simple. We now, instead of doing a complicated convolution, we only do it at times in the frequency domain. And you probably have heard many talks about structured illumination microscopy, in which when we put an structured image, put an structured illumination on another structure, fine structure, we can detect its low frequency because of the Maury effect. And by doing so, we can generate an image with twice the resolution. So let's simulate this process. In an structured illumination, we're gonna use an sinusoidal or cosine function to illuminate our sample. But the cosine function, once again, because it is projected using the same objective lens, we will convolute it with an PSF of this lens. And the imaging, once again, is what we get from this convolutes by the point spread function. And this rather complicated process can be simplified or can be translated into the frequency domain. So the frequency of the sample convolutes three components, which is the cosine, the three elements of the cosine function, the, the DC component, as well as the two AC components, and then modulated by the OTF. So we always convert times into convolution and convolution into times during this Fourier transform. And the imaging is very simple. We once again times the OTF. Okay, so oops, here so let's first take a look at how we generate a structured illumination. So first, we will generate an array with m equal to 512 and xx, yy, and mesh grid, and then we use this cosine function to generate the illumination pattern, and then we plot it, and then we do the Fourier FFT2, which is a 2D Fourier transform, and then we FFT shift and see the frequency component of that, and we will write it to a cosine function. Okay. Now, if we plot any of the illumination, we will see any of the Fourier transform. We will see this component, and let's show the illumination. As you can see, it is an very dense cosine function. We can change the frequency by doing so. sim illumination. Okay, this is an um, illumination with 3 over 16. This is 2 over 16. 1. Okay, you can see we can constantly change the period of this illumination pattern by doing so. And here is the 116, 16, 1 over 16, etc. We can see the corresponding Fourier transform here because I use 1 plus cosine to generate the illumination pattern to avoid the negative part because we cannot excite anything with negative values. So that's why we have a strong zero components. And it actually mimics the physical nature of an illumination. And we will find that we need to show, if we show the image, you will find that it is indeed um, okay. This is the pattern and the three components, corresponding components in the Fourier domain. Okay, next we're gonna read in and here I have an pre-prepared image of the sinusoidal function tilted by using Photoshop. So cosine. Okay, this cosine one dot GPG is an prepared sample that I'm going to do the demonstration. So it is generated with Photoshop by rotating my cosine pattern, horizontal cosine pattern. And let's see the codes. If I read it, the cosine one, we can do it. Actually, we can do it together. You read cos1.jpg. Proceed to double illumination and ff2 means add it to I defined an function handler of ff2 figure. You will figure subplot 2 by 3 1, which is my illumination, then with my gradient image and selected uh, resulting image. The Fourier FFT to FFT shift IL illumination. So the illumination, we have to zoom in. Otherwise, it can only show one spot. There are actually, I'm gonna do this. You can see now there are 3 spots pops up. So due to the resolution, it only shows one, but it's fine. Fifth is the sample, and the sixth is the DET. Okay. Oops. I should do a log. Because of the scale, we have to give it a log scale. It will be shifted to the located coordinate of this illumination by here and here. 3 copies will be generated by this. And of course, we can save the history. We can save it to a new script. Oops. Save it to a new script. S equal to ingrid cameraman that we are familiar with, and resize S to be 512 to 512. Okay, as you can see now, I illuminate the cameraman uh, with these components, and it will shift the original one to the new coordinates. Uh, oh, here once again, because I forget to log, so the pop-up doesn't give me the correct result. As you can see here, if my component is shifted here, it will be generate 3 copies here. And if I change the frequency, it will also shift this back to the generate 3 new copies. Okay, this is the principle uh, of the structured illumination in this regard. And in the structured illumination, we will have 3 illumination components, which will shift the original sample frequency into 3 copies. And our task is to solve these components from the overlap. And because we have 3 unknowns, dk minus p, and dk plus p, we set the angles to be the phase angle to the phase to 0, 120, and 240, and we can have E1, E2, and E3, 3 images to solve the 3 unknowns, and which can be written as a matrix of E equals to A times X. And to calculate the unknowns, we can use the matrix calculation X equal to M, the inverse A times E. So then we stitch all the components together, and however, this is only from one direction. And in order to generate a homogeneous image, we will require 2 to 3 directions. So normally horizontal and 60-degree and 120-degree. And for each direction, you will do 3 times. So it's at least 9 images to be taken. So I'm going to give you a demonstration about the simulation and the reconstruction using the famous picture of Lena. So this is the wide field result, and this is the sim result. Now let's go. Before that, I need to find my uh, JPEG, and m equal to 512. I'm gonna resize it to 512 by 512. And then I generate a mesh grid for illumination, and then I create a cell structure of 4 by 3 to record the process. And my PSF has a width of up to and the size of 512 by 512. And then the OTF2 is the FFT shift. And then once I have the OTF, and I will cut the central part of my PSF, and I use a function called edge taper to remove the edge effect during the FFT process. And once again, FFT shift FFT to the the original image, which is in zero.